Well, good morning, good evening, or good afternoon, everyone. We're going to wait about just one more minute as people kind of file in for our webinar this afternoon. Okay, so let's go ahead and get started. So welcome to the webinar. My name is Tony Remejat. I'm the director of the Green Bank Observatory. I'm just going to give you just a very quick update on what's happening in Green Bank these days. So we've been about 2 months now of observing as we came back from our shutdown from our maintenance and infrastructure improvements that happened over the summer. So it's a lot of business as usual at this point. Right now, happening this week, we have the GBO Observer Training Workshop that's happening virtually. You will have another opportunity to participate in the workshop next spring, both here in Green Bank and also next fall for another virtual workshop. So keep out a lookout for that. We also encourage everyone to come out to the AAS meeting and check us out at the booth, the NRAO booth. We're going to have some pretty unique swag out there for Phoenix, so I hope everyone could participate and come and join us. And just as a note for everyone, next week, mid next week or so, you're going to be getting your acceptance letters for your 26A disposition for your 26A proposals. So keep a lookout for the disposition letters that should be coming out about mid-week next week, and then work with your project friend to get those projects set up and ready to observe starting early next year. So that's all I have today. So I'm going to turn it over to Dave to introduce our speaker.
Hi, sorry, I got my FastX, but not FastX. Zoom blew up, but I'm back. It's my pleasure to introduce our speaker today. It's Eric Koch, and he's from he works now at NRAO, and he'll be giving a presentation on the local group L-band survey. So Eric, go ahead and put your slides up and share your screen. And I would like to remind the participants we'll answer questions at the end of the presentation. And if you have questions, please put them into the Q&A box, and we'll address them at the end of the presentation. So, yep, we can see your slides, Eric. They look good. So feel free to take it away.
Perfect. Thanks, David. So hi, everyone. Yes, so I've recently joined NRAO a few months ago, working on the ngVLA project. And so this talk is going to be focused on this local group L-band survey, or LGLBS, the acronym that you can never remember. Very convenient. And so there's two things I want to convey in this short talk today. One is just a brief overview of what the project goals are and sort of where we are in this project. And that first part is going to be pretty much dominated by the VLA aspect of it. But given this is for the Green Bank Observatory, the second half is going to be focusing on some of the results, demonstrating how crucial it is for a number of the science goals to have the short spacing from the GBT for the H1. So that's where we're going today. Just to set the context, LGLBS is looking at their nearest galaxies to better understand this much broader problem of galactic ecosystems. And what I mean by that is, at least on this particular scale, looking at how galaxies interact with their nearby environments, their circumgalactic medium, and in particular, how we understand the process of how the cold interstellar gas goes through this rapid cycling of star formation, particularly for massive stars, and trying to link all these different processes and scales together. And so one of the most important aspects of LGLBS and the capabilities of the VLA and L-band is that there are aspects of most of these processes that we can trace from this set of observations. So in particular, this is the 21 centimeter line, being able to bridge from high column density sensitivity to high spatial resolution, giving us an understanding of how molecular clouds form. And the other side of this, from the L-band continuum, we're tracing the free emission from H2 regions, so giving us insights into an almost extinction-free view of star formation, as well as the synchrotron emission being driven by supernova remnants. And in particular for this talk and a couple of results that I'll show here, it's really this low surface brightness that I'm going to be focusing on, and why the short spacing that the GBT provides is really crucial for this science. So a brief overview, right? So LGLBS's goal is to map the atomic gas, the H2 regions, and the supernova remnants in our 6 nearest neighbors, accessible to both the VLA and the GBT. And so the time cost and the focus of the survey as a whole is really its VLA aspect. So about 5 years ago, or I guess 6 years ago, there was a call for these extra large programs for the VLA to support. We're very fortunate that ours was selected, and we're very thankful for the support of the VLA and the VLA staff in enabling such a large program. So this is about 1,800 hours from these local group galaxies. We've combined that with an additional 500 hours of archival data. So the sort of sticker shock price is the VLA component. And the GBT component is a few hundred hours or so, but luckily this was already available in the archive from a combination of other types of projects or things that are subsets of the team had been investigating in the first place. And I think it really speaks to just how incredible the GBT is at this H1 mapping, that this isn't a large amount of time to match the VLA. This was simply what was already available from a hodgepodge of projects just sitting in the archive. So there's 6 galaxies that LGLBS covers. They are the ones that you probably most expect for studies of the local group. Of course, this is M31 and M33 as our larger star-forming galaxies. And then we also look at 4 star-forming dwarf galaxies that you can see in the second row here. The bottom row is showing the full spatial coverage. So each circle that you see there is one of the VLA primary beams. So as you can imagine, M31 dominates this because it's so large on the sky. How do we come up with this sample? Well, this is actually pretty simple. They are the 6 closest gas-rich galaxies that are observable in the northern hemisphere. So this plot is showing H1 mass as a function of distance from the Milky Way. All these blue points come from a larger compilation of samples by Mary Putman. And essentially, we have taken a mass cut and looked at where we have galaxies within about a megaparsec, and you get these 6 galaxies. And so this is basically the best that we can do for the nearest targets to study the H1 and radio continuum, where we can resolve fine scales with what we can currently do with the VLA. Now, compared to previous surveys, one of the major reasons that, or capabilities that enabled this survey was the upgraded Jansky VLA's spectral capability. So at the same time, we can collect the entire L-band continuum from 1 to 2 gigahertz with full polarization. And we can pick up a number of spectral lines, key science here enabled by the 21 centimeter line, while still having enough bandwidth that we can cover the entire galaxy at once, and being able to have very fine spectral resolution. So this was really key for some of the motivation here. And just to give you a sense, this 0.4 kilometer per second resolution that maps to a thermal line width of about 100 Kelvin. So the idea being is that you're sensitive to very narrow line widths that you would expect from the cold neutral medium. In addition to that, we have 4 hydroxyl lines to start looking for OH masers in these targets. And then as a tertiary goal, we have a number of hydrogen radio recombination lines, which we, even with all this time, we expect that those are going to be faint and difficult to detect. So I'll briefly just note some of the key goals for the radio continuum. The target overall is about 2 arc seconds within a megaparsec. For our samples, this maps to about 8 parsecs. And we have sufficient sensitivity, about 2 microjansky per beam, that this should allow us to detect every H2 region driven by an individual B0 star. It should also allow us to detect effectively every radio bright supernova remnant that are currently in these galaxies. So this is just a single pointing. This is work that Sumit Sarbatikari led. This was actually our demonstration to help motivate the project as a whole, showing that we can get down to 2 arc seconds at our nominal noise level with the high dynamic range that is especially needed in a large source like M31. As you can see with some of these double lobe background AGN, there's quite a number of confusing sources in the field, so this was an important test. I want to briefly show a brand new image that's actually exploring the polarized continuum with our new data. This is a brand new map. This is work led by Timea Koch, who's a postdoc at MPIA. And this is combining all of our 49 pointings of M31 and looking at the polarized continuum in a lot more depth than was previously available in other surveys. So there's a number of radio continuum science goals that are going on as well here. I'm going to shift though to talking just about the 21 centimeter. Uh, and that's all coming from the GBT. And so these are our these comprise our first data release. So you can actually go and grab all of these data if you're so inclined. Um, and they really represent what I think is just going to be the best view of the atomic gas across the local group, at least until the next generation of interferometers like the ngVLA is able to come online. Just to give you a sense of where we're going, pushing this spatial resolution to the most that we can do with current interferometers. This is picking out a small region in NGC 6822, one of our dwarf galaxies. It's actually slightly higher resolution than the images that I showed before, but now we're looking at about a half a kiloparsec aside box. So the top is showing 50 parsecs, the bottom is showing 10 parsecs, and this is essentially the highest that we can push current interferometers. At this target's distance, this is about 4 arc seconds, right? And so this is what we get when we take about 50 hours of time for a single pointing in all 4 of the VLA's configurations. So reasonably, this is the best that we can do at the highest resolution while still having enough surface brightness sensitivity to be able to map out the structures of this, what becomes this very bubble-dominated and filamentary looking structure at high resolution. So this is where the project is going forward. There's an upcoming paper led by Nick Pingle that's going to be presenting a number of the high resolution images. But for the rest of this talk, I'm going to focus again on the low surface brightness components and where the GBT short spacing is really critical. So this is a map that was actually from my PhD. So this is pre-LGLBS. So it was part of our pathfinders to demonstrate what was possible with revisiting these local group and well-known targets once the VLA's upgrade had been completed. And so one of the results that we found here, just again to demonstrate the importance of the short spacing, was highlighted in this paper here. So I'm picking out 2 individual spectra, and their locations are in the northern and southern hemisphere. You can see them pointing to the map on the side. And the difference here is in black is what we have when there's a combined with the short spacing from the GBT. The gray line that is consistently below it is showing what it looks like with the VLA only. And so we have an excess, but the excess is not symmetric. And that's something that we really keyed in on for this analysis. What we find is that including the short spacing always leads to these asymmetric tails. And these tails point preferentially towards the systemic velocity depending on where they're located in the galaxy. So in the northern hemisphere, that's a tail that is red-shifted. In the southern hemisphere, for the most part, that's a blue-shifted tail. And that's what this map on the side is demonstrating. This is a measure of the asymmetry in these H1 spectra. And you can see that, there's some local variations, but for the most part, the entire northern limb is red-shifted, the southern limb is blue-shifted. And this has a really simple source. It just means that we have enough sensitivity to be tracing more diffuse H1 gas off of the midplane of the galaxy. So what's happening here is the bright H1, right, is preferentially at the midplane. So it is rotating at the normal circular rotation velocity of the galaxy. As you move off of that and where there's the more diffuse gas, that circular rotation velocity is just going to be less. So you preferentially get these asymmetric tails that are closest to the systemic velocity as a result. So what we found in this earlier survey was just demonstrating that this is enough sensitivity and the short spacing is critical to be picking up this large-scale diffuse component. So now that we have LGLBS, we want to revisit this. What does this look like with our better sensitivity, more broad coverage with the VLA? And the spatial image itself is actually tells most of the story. So here's what we had, again, combining VLA with the GBT. When we add this in with substantially more time of short baselines with the VLA, this is the same image we get. These are integrated intensities. They've been treated in the same way, but suddenly there's significantly more large-scale diffuse structure. And so this is one of the portions that the team is looking at. And in a nutshell, what this is telling us is that we're actually recovering a well-known component from other single dish surveys, that there's this larger warp disk in M33. We're just detecting it at higher resolution for essentially the first time. So I'm showing here work led by Emma Kleiner. Emma is a master's student at CUNY, working with me and Julianne Del Canton, and she's been modeling M33 with these new data. That's what the three panels are showing here. The left is the centroid. The center is just a simple rotating disk model. And what we can see is these outer regions where you start to see the edge of the warp disk have obviously different kinematics. The difference here is being shown in the residual that's on the far side. Now, across all of these panels are also these contours. And the other portion that is not as obvious from just these projected views of the galaxy is that we're also detecting a number of anomalous H1 clouds. So the contours that you see in the center correspond to these anomalous clouds. Now, these have been noted before in M33, including in archival VLA data from about 20 years ago. I could also see them in the pre-LGLBS data, but we had to stack over a large velocity range just to get sort of basic detections. The LGLBS data just has enough sensitivity that we can do this within just the data cube with standard signal masking approaches, and we suddenly have all of these clouds start to pop out. And so this is an ongoing project that Emma's leading, but their velocities are suggestive that we're actually finding some clouds that are likely leading to cold gas accretion onto M33's disk. So potentially giving us some constraints on the amount of cold gas coming in that might be sustaining star formation in this galaxy over a longer period of time. So that's essentially what's being shown in this map here. The background is just the rotating disk model. We have two blue, red color bars. So the second one, and where you can see offset in these individual features, this is the anomalous component. So they vary quite a bit from the circular rotation velocity, but they remain coherent if you were to, for example, subtract out the rotation curve. So we're quite confident that they are indeed associated with M33 as a whole. And the last thing I'll point out here is just that large blue feature that you see at the bottom. This is this several kiloparsec long filament. It appears to be fairly consistent in its kinematics. And so what Emma is now working on is understanding the properties of this feature and being able to constrain the gas accretion rate from it. And so with that, I'll just summarize here. So again, we have our first data release out. Those were the 100 parsec maps that I was showing before. They are available via CanFAR. You can find it with that QR link there. And then some of the results that I showed here is just demonstrating that the GBT short spacing is really critical, especially for looking at this sort of diffuse component that's surrounding these galaxies. And that's giving us some idea of how cold gas is accreting or potentially accreting onto these galaxies, and in some cases, potentially outflows as well. So this is work in progress, but this and many other LGLBS results should be coming out over the next year. So thank you, and I'm happy to take some questions.
Yeah, thank you very much, Eric, for these images are spectacular. So really appreciate it. Yeah, we have some questions coming in. The first question is, could the lagging of the H1 rotation observed also be related to possible non-homogeneous, dark matter density gradients?
I am not particularly sure. What I suspect is that there is a portion of that lagging emission that's actually related to this larger scale warp disk. They are pretty similar kinematic wise, and this is something that we need to test, but I think it's more likely to do with whatever is causing that warp disk as a whole. Perhaps that's related to dark matter. My understanding is this is very much an open question within the field of just understanding the structure of M33 in the local group.
Okay, another question. Is the streamer analogous to the Magellantic stream?
That is a great question. I think probably, I don't know the total mass of the Magellanic Stream off the top of my head. I think it's pretty clear, right, that that is dominated by the interactions between the Magellanic Clouds and the Milky Way, right? There's some speculation that there's a missing satellite, dwarf galaxy satellite around M33. Lambda CDM predicts that there should be a non-zero value, yet we haven't found a potential dwarf galaxy. So perhaps that is actually related to what we're seeing here. On the other hand, this streamer looks pretty similar to another fairly isolated flocculent galaxy, NGC 2403. And that is a far more isolated system, but it appears that it also has a filament that looks kind of like this, just, it's a little bit farther away, so we don't have quite the same resolution. So I think there's still some basic questions that we should try to answer with what these features.
A follow-up question. Do you have an estimate on the mass? I know you guys are still analyzing of that sort of that filament structure. Have you did ballpark numbers or made an estimate of that yet? Just out of
Probably
curiosity.
about 5 times 10 to the 6 or 10 to the 7. So
okay. So that's pretty substantial, actually.
Yeah, of course, we're assuming the distance to M33. It does look like it's associated, but that's about 1% of the total H1 mass in M33 as a whole.
Okay. Another question. Would an observer who was inside M31 perceive these anomalous H1 clouds sort of the same way we perceive high velocity clouds?
Some of them, yes. Because they are offset by tens of kilometers per second or more than tens, but 50 to 100. So I think they would be similar to high velocity clouds. We're not sensitive to, I guess, the entire population that is often looked at in Milky Way surveys. A number of these are probably closer to intermediate velocity clouds. One of the difficulties that we have so this is fairly straightforward in M33 because its velocity is sufficiently offset from any Milky Way foreground. We should be able to do something similar in, for example, M31 that has a lot more H1 mass, but because it overlaps a lot more with the Milky Way, it's a little bit more difficult to assign what is just the Milky Way foreground versus something that's actually associated with M31.
Okay. A question, do you also have OH results? And if so, what are they with the H1?
So we do have that data. Sensitivity wise, we are effectively getting into the upper tail of the OH maser luminosity function from the Milky Way. So we're starting to recover a handful of sources, just compact sources.
Okay.
I think we could do some clever stacking. Potentially, this is something a new Jansky fellow at NRAO might be doing. We could be doing some stacking experiments to see if we could tease out the diffuse component. But that, I think, is something that we need to look into in a little bit more depth. It's going to be challenging.
Okay. How do these findings relate to similar, if any, farther beyond the local group galaxies?
Yeah, the sort of resolved extraplanar structure, NGC 2403 that I mentioned before, I think is one of the best studied ones. I think one of the difficulties for anything that say doesn't have a physical resolution of a kiloparsec or better is that it's going to be very difficult to separate out these features. So you get a lot of blending from having the much larger beam. So I would suspect that other surveys for more distant galaxies are picking up some of these features. Whether or not we can clearly separate them out spatially or spectrally, I think is the question. So one thing that we could do with these data is of course smooth it to something more similar to what you'd see at 10 megaparsecs or 20 and start to see if they are just blended spectrally. That's not something we've looked into as much so far.
Okay, and there's a question, have you checked the rotation curve? You've certainly measured it.
Yeah, so we have measured it from the pre-LGLBS data. So the first results that I was showing come from a new rotation curve model that was fit. We can, of course, fit it with the new data. I suspect that the overall structure is really not going to look all that different from what is already in the literature. Um, I think the novel parts here will be for M33 being able to have this resolved view of we transition from sort of the main disk to the warp disk. It'd be interesting to see the interaction there. Um, and looking at some of the non-circular structure as we can get down to a much smaller spatial resolution. Those, I think, are the most valuable places that LGLBS can push on.
And then another question, any polarization measure emission data that you've collected and to measure magnetic fields, make it even more ambitious besides just stacking on your OH?
That is very ambitious. I I would suggest whoever's suggesting that to get in contact with us because I don't think that's something that anyone on the team is currently looking at. It'd be interesting to see if we could. I suspect that would be very ambitious. We also don't have full polarization data
Okay, that's why.
in the way that
Okay,
we
that
pick
might be
it.
the answer to that question there.
Okay, yeah. So, you could try to look at the two different components, but we don't have the cross terms for those.
Yeah, okay. Another interesting question here is, are there any continuum sources bright enough for you to detect absorption in H1 or OH?
Yeah, great question. So this is actually, we're doing this in a couple of the dwarf galaxies so far. This is a paper that is now published led by Nick Pingle. And what is being shown here is the H1 absorption towards a number of background continuum sources. That's what's being shown in the top. And here it is with the surrounding emission. So we are able to start probing this with a few lines of sight within these dwarf galaxies. In this particular paper, we only had, I think it was 2 or 3 detections that were certainly associated with 6822. There's a number of others because there's a strong Milky Way foreground. You can see in these green components where we do pick up the Milky Way foreground. Um, and similarly, so this is the same image as before. The one on the left is a paper that is close to some, or sorry, it has been submitted by Io Stelea, who's a PhD student at Wisconsin. And the 3 stars that you see here are the 3 places we've measured H1 absorption within IC10. That one is kind of interesting. They're not background sources. They're actually the embedded young massive clusters that happen to be in this galaxy. So a few sources were able to do it. The important part here is these are some of the first low metallicity detections in these dwarfs beyond the Magellanic Clouds. We can do this in M31 and M33 as 2. That's going to be a number of more sources, sort of at the level of dozens. That is still a work in progress.
Okay, well, thank you. I think that will end our Q&A session. I just want to thank you again for sharing. This data looks spectacular, the combination of the VLA and the GBT data. It's just awesome to see such high resolution H1 observations. So thank you very much. And thank everybody for participating. We'll be back in 2 weeks, and at that time, Evan Lewis from West Virginia University will be talking about GBO observations of a magnetar. So thank you, everybody. And thank you again, Eric, for an excellent talk.
Thanks, everyone.
Have a good day.